Yeah, welcome everyone for my presentation at the IPDPS conference online, not in Portland, for the Heterogeneity in Computing workshop. My name is Maurice Riedel. I'm a professor at the University of Iceland and also have a research group at the Juelich Supercomputing Center in Germany. So this paper is really a collaboration between these two organizations, and this is also under the umbrella of the EHPC National Competence Center for HPC and AI in Iceland, which explains a little bit all these different basically logos here. So they are in one way or another contributed also to fundings that of basically all the PhDs had to get in order to get all the practice and experience in parallel and scalable machine learning with the heterogeneous modular supercomputing architecture. What this is, there are lots of words included. We will basically review a little bit when we come to the short introduction, where we reflect a little bit why we need the modular supercomputing architecture, why basically is parallel and scalable machine learning and deep learning something that can really benefit when using the MSA. We will have some reasoning then why the MSA is an important part here in the strategy in Europe and also in the Jülich Supercomputing Center in particular with its implementation. Then we would have some practice and experiences really from real different areas of applications. Today we focus here on remote sensing and health applications. A little bit the modules are here already as a sneak preview for you. Of course, this is the talk that cannot go into the details of all the different papers that you have essentially also for this conference, but we bring you a lot of references for more, let's say, investigations. And of course, you can also contact us if you have more questions. So after a summary there, you see all the different references, which are also very important to put more, let's say, emphasis on different areas inside the practice and experience of using our, let's say, system #1 in Europe, JUWELS, in practice. Good, but let's come to the short introduction, and this should really motivate why we in Iceland here thinking about modular supercomputers. The first reasoning is really we have a very strong core of community of users, which are maybe not basically so many compared to the key central ones in Europe, where essentially here having 53 scientific experts and research groups. But the key message to take away is really they do research on very different areas of science and engineering. And of course, with this comes also extremely different requirements to HPC systems today. So this is one of the core ideas why modules, different modules of HPC systems that we will allude to in this talk are really required. This is then basically even more clear if we bridge then to industry. We have the simulation data labs here that we create in the University of Iceland and at the University of Reykjavik and throughout Iceland. But as you see on the experience that already the Jülich Supercomputing Center, for instance, brings in Germany, then you also have lots of different users in many different areas of science and then also requiring very different HPC systems. And we will come to this. So essentially, we talk about this international cooperation, and we have there not only this interesting cooperation between this, Jülich Supercomputing Center and University of Iceland, of course, as part of being large EU projects like DPS, EOS Nordic, or the more recently funded RAISE Center of Excellence, we really collaborate, of course, with much more players, and all of them reflected a little bit the fact that the application requirements are very different. Now, in the light of the MSA, also this element is quite interesting. So you see that Iceland is even contributing to the LUMI supercomputer in Finland and is part of it. And here you see also different modules in a sense reflected in partitions. So also the LUMI supercomputer in a way has a CPU partition, the GPU partitions. So it's also a very modular approach, also planning for a LUMI Q with a quantum module. We will come back also later. So essentially, this just putting you some examples why MSA is needed. And while we see here below in this interesting video, the, let's say, evolution of deep learning, I would like just to briefly explain what we mean with machine and deep learning, because these words are maybe not to everyone here in the HPC community completely clear. So you would have artificial intelligence, which also includes robotics and a large area of technology. So when we talk about machine learning, we really have a subset of that, which is more or less concerned from learning from data, right? You don't have conventionally a structure of a, let's say, software or software engineering. In this sense, you rather think about learning from data without really programming it. Of course, you do it in programming languages like Python, but you have other structures like training, then testing, or training and inference. You have then sometimes validation, and all of them require computing. When it comes then to deep learning, you see here a little bit, interestingly enough now, the idea of a multi-layer perceptron. If I stop here, you see different, essentially, neurons. This is artificial neural networks we had already, let's say, in the 70s and so on. And were quite effective, but always limited also in terms of computing. So essentially, this was just neurons in different layers. But when we talk about deep learning, we talk really about very smart layers. We talk about different neural network architectures, not anymore just putting deeper neurons together and then you have a deep learning network. That's not all of it. So to really understand deep learning, you have to think about that essentially you have very smart layers like those that in CNNs, convolutional neural networks that you will basically see here now in the video, can detect features. So the ability to really learn these features in the data is really one key theme in basically deep learning. You see this very nicely here in the idea of this particular character recognition problem, which is a very trivial problem, but essentially saying you, instead of, just having just neurons, you have here feature maps, you have downsampling, subsampling, and then the convolution operations. So all of that is contributing to the success of deep learning today. You would use this with different methods in machine learning classification, meaning a new data item in, different groups that are already existing, and you want to understand, you can create a system that can do this, or clustering. You don't have really a basically new system, new basically group, but you can explain it a little bit with similarity measures, Euclidean distance, ruler distance, that these are different clusters, or basically trends, regression techniques, and so forth. So this is really AI and computing. Now we bring that together on this slides. I was asked once by the Federal Parliament in Germany to do this, to bring big data together with high performance computing and then together with deep learning. What does it mean? And here we can see this very nicely, that in the traditional classifiers, when you're not really swimming in data, then essentially you still want to use them. They're very good still to use. However, when it comes basically to very large data sets, you have increasingly problems with memory. The time to solution takes a long time. And also the accuracy is quite limited because deep learning networks and neural networks have shown that they have much better accuracy today. However, you have to pay the price for it, which is this red footprint, right? The better and the bolder the deep learning network is, usually you have an increase in training time of those. And that's where really HPC has a very large footprint. Interconnecting GPUs is here the cutting edge, maybe on the top. And then you also get essentially the high accuracy. However, you see here in the beginning, when you have not really much data, then you have quite some problems of using deep learning networks. You can do data augmentation techniques, but still, essentially, then you enrich the data set and grow out of this data set volume. In a sense, this really shows you all these connections together, and not forgetting that, of course, we want to use these things that you see here with really different application areas. So much for the introduction. Let's come to the heterogeneous modular supercomputing architecture. And one of the reasoning is really the energy efficiency that is required in EU. You see a very good example comparison to Summit, which is #1 in US, where there's #1 in Europe. From the kilowatt perspective, you can see that's a clear indicator that we in Europe are quite limited there. So that's a very key theme and key priority here in Europe to drive it. But JUWELS is still very powerful, as you see, and can actually have enormous energy efficiency, right? Thinking about the green 500, the other list where nobody is talking about, there we are, of course, #1. So essentially, this is one motivation, the energy efficiency. But again, when you think about then all these different users that we are already explaining in the beginning as a motivation, right? They have very different requirements for a system like JUWELS from different applications. And of course, as it mostly is government machines we have in Europe, the users and the application have a strong voice. And in this sense, this is something we really have to engage in, because Europe maybe at large doesn't have so much money to put on these systems, right? You see Summit is a very more or less homogeneous systems, more and more GPUs per node, and then really scaling up is many, many different nodes. Of course, a bit is JUWELS Booster here comparable, but then we have also the other modules I will talk about. And these modules have been designed really by listening to applications, by listening to application developers for co-design, as we call it in Europe, leading to a cluster module with very high single thread performance CPUs, leading to a booster that is actually much more about highly scalable jobs. Many different GPUs, for instance, interconnected and scaling up highly. Data analytics module means large memory for things like Apache Spark, and then we have the scalable storage service module. Research we perform on this is also the network attached memory. It's quite interesting, where you basically, as a research group leader in AI or machine learning, you put your data on the network, and then your whole research group members can always access it via the network in this memory, instead of dropping it always essentially to disk or to file. And then when it comes to scalability beyond NVLink and NV switches, the GPU direct interfaces, of course, are very important, and we do some research there using essentially the host CPU more or less like a network controller, which can be then, let's say, a cheaper CPU, and instead you put the emphasis here on boosting essentially interconnects between the kernels to avoid this offloading essentially from the host CPU always to the GPU. But these are all, let's say, different areas of research, which is not the key priority of this talk today. Let us come a little bit again to the idea of the implementation of the MSA and the different modules. As I said, we have these different 4 modules already explained, but this is also a future-looking design where we already do our baby steps, so to speak, on quantum modules right now, and where we also will see in the future neuromorphic chips, very specific chips for specific problems. And the way you want to use it is maybe essentially training, time-consuming training with CPUs on the cluster and then inference on the module, or you have essentially basically a very tough optimization problem in machine learning, and you would use a quantum module for that. So essentially we talk about the quantum system here not as a general purpose system, but rather that the general purpose system at some point in time, like an accelerator today, will then essentially use a quantum module for very specific optimization problem solving, and then comes back to the other module for performing the general purpose part. You see also here again the Jülich Supercomputing Center perspective on all the different application fields which contributed in one way or another really to this application co-design, and with this within the DPS project really to the idea of creating such a modular setup. And it works. We had the JUWELS cluster module before, we had a Jureka system. We now have a JUWELS booster modules, really satisfying the needs of many different application scientists all together. And we can see also the rise of a exascale system, potentially 2023 in Jülich, funded by EU and also Germany. And then basically also in using the MSA design. When you want to know more about this, because in this, let's say, short conference talk with application experience, I cannot go into the technical details in all of these, but you see here essentially a very nice YouTube video link that you can have to look more in detail. For the numbers perspective, I think that's not so much interesting. You can see that on the web page. We don't have to talk about this too much. This is, let's say, raw information. You can imagine the cluster module has good CPUs, as I was alluding to, good memory, and then also the booster module here. The emphasis is very clearly, of course, essentially on the new Ampere GPUs, and of course on the HBM memory that you have there as well. So the data analytics module, just for your, let's say, reference, is something we don't have in JUWELS yet. You see it in the paper. We still there use the deep MSA prototype with the num and elements. So this is something, of course, also where JUWELS in the future might be advanced, or another modular supercomputing architecture in Jülich. So I stop here the time lapse essentially on this installation of the JUWELS system, because I think many of you here in the HPC have already HPC workshop have already seen something like this. So let's have a little bit of look on the case studies with remote sensing applications. So this is research performed largely by the Simulation and Data Lab Remote Sensing in Iceland, but also, of course, as we said, in close collaboration with Jülich and many others, Trento and Extremadura and many different players internationally. Remote sensing essentially can be explained very briefly here for the HPC community in a way that you would have satellites. They provide you with hyperspectral data sets, multispectral data sets. In other words, you have really spectral information of each of the pixels that you see here, essentially on the land cover. So it's not only, let's say, 2D, we really have here a multidimensional problem, 224, you see there's spectral images essentially taken at the same time. And this different wavelengths and this different spectral channels give you then essentially with the reflection, the indicator if it's soil, water, vegetation, so you can have information about the material from the spectral information. And this is of course interesting. For instance, if you do land cover classification, that's an example here for the paper we brought. There are different ones, and the idea of machine learning is then to really find a classifier that can use not only the spectral information, but also the spatial information that you would have, right? So the neighborhood pixel gives you also indicators on the material, basically, that you have as a land cover, and creating those basically maps. Here the challenges often rely in mixed pixel, unbalanced land cover classes. So lots of challenges along the way, leaving along, of course, also high resolution data today. And you see remote sensing can be used by quite many of the different applications here, from urban planning to smart cities, or as basically also to disaster management. Now, when it comes to an overview, what is now the case study research about? We want to sketch a little bit how the blueprint of this modular setup looks like, also from the library's perspective on this layer, and also on the key hardware technologies on the lowest layer here, right? Of course, it starts all with a very processing intensive applications. We bring you here today as an example Earth land cover classification, but equally you can use remote sensing for exploration of oil reservoirs or near real-time processing even on the satellite on board missions. When it talks about this classification, this is a timely process. So it really needs not only big data and the models, it needs lots of HPC, which brings us to technologies where we do then distributed training of ResNet 50, I will alluding to. You see here the modular supercomputing JUWELS, you see the DAM, and of course the details are much more in the paper. So I go a bit quicker here through this. You see the LUMI supercomputer, which is also in a way a modular supercomputer. And so currently these systems are basically here, modular supercomputing JUWELS is accessible via Praise, while in the future this might be all Euro HPC systems here in Europe. And you see also we bridge nicely to commercial cloud vendors with our container environment that works on JUWELS. We can basically have interoperability with Docker container environments that are available, for instance, in the AWS space in the cloud, but also in MS Azure, for example. So when it comes to libraries, we have a parallel support vector machine we actually maintain in Jülich that is used for applications. Of course, distributed training is a very highly topic with machine learning libraries like TensorFlow, PyTorch. We do distributed training a lot with Horovod. We also started to use DeepSpeed a bit to get our early, let's say, experience with it, but we cannot report very much from it. Interactive access using Jupyter and Python, we see systems is possible. And of course, we also bridge to Apache Spark here and there on the data analytics module, for example, or basically when it comes to cloud setups. The key ingredients here, you have seen the network attached memory we do research with, which means in general, we expect more innovative memory hierarchies. Non-volatile memory, of course, has a very big impact nowadays. Multi-core processing, many core accelerators, of course, are a key subject. We were making now the move from Kepler, Pascal, Volta, finally to Ampere. You see there's also lots of different technologies where the modular supercomputing architecture really is leveraging all of these technologies. So when it comes to processing intensive for HPC, for you to understand where are the troubles, where is a HPC really needed, we use it again and again for parameter optimization, for hyperparameter tuning, as we call it. So you would have deep neural networks, and the details are not so important for you. It's just these layers need training of their weights. They still have all their connections to each other. And this is a loaded process, but you also need to know how big essentially such a tensor would be that you would basically put through the different network. So talk about feature maps, how basically large are those? The optimizers used. So essentially all what you see in the red element is things you choose. And with choosing them, we never know what is the right thing to do. Of course, you have some experience, but essentially you need HPC to really try out a lot of these parameters again and again and again. And this goes even more deeper if you want to combine maybe also different approaches. You see here, we're combining deep learning in this particular paper, for instance, also with support vector machines, so more traditional classifier within the different layers. So also there are parameters to pick again. And this is really a tough, basically, approach in thinking about what hyperparameter tuning can be. In the future, we will see neural architecture search arising, which really will stress the need for HPC in the future. Then when it comes to our own experience right now, again, from thinking about the modular supercomputing architecture, you see here an example, which was still on our Volta GPUs, where we use Horowot, essentially a distributed training tool for our AI tools, and it works very nicely on JUWELS with 24 nodes and 4 GPUs. Interestingly enough, Horowot still uses MPI or reduce on the MPI standard inherently, and this really breaks down a lot of training time to just a very short time, considering the amount that ResNet 50 is a very tough network to train with 25.6 millions. And this is just one setup. Think about that you have to find these hyperparameters I was alluding to. Maybe you need a couple less layers, maybe a couple of more layers. So this is, of course, a really key challenge. But I also want to talk a little bit about the quantum machine learning, just a bit of saying this will be more used like an accelerator type, where you say for some problems like the optimization problem inherent in a support vector machine, quadratic programming, this is something where we have a quantum SVM that then can help to solve this optimization problem and is still then coming back to the general purpose part of the application on the modular supercomputing JUWELS. So this is the early steps. Quantum computing is quite a disruptive technology. So I have a complete tutorial here as part of the UTMS and IT conference here in Iceland, but we were using it already and the details are in the paper and a couple of those application-oriented papers at the IGAS conferences. So that works quite nicely, firstly using the 2000 qubits and then the 5000 qubits with the D-Wave Ocean API in conjunction with our setups. But towards basically the second part, just a couple of slides around health applications. Here we do lots of research in the simulation and data lab, health and medicine as well in Iceland, also collaborating closely with Germany, with many different hospitals in the SMIS project. And there we basically have also requirements for hyperparameter tuning of mechanistic models that you essentially see in a couple of the slides. But to really have an overview what's happening with the modular supercomputing architecture in that context, you see that the same setup is more or less used also for health applications. We have still distributed training. We have our network attached memory, the accelerators, Jupyter. Here and there, some things change. Maybe here we use more Git-based data management with DataLat in the neuroscience area, for instance. But also the containers play a very huge role today, which actually also works. And of course, for time series analysis, not everything is image analysis, as we have seen in remote sensing. We have also good experiences with the architectures, and including also COVID-19 chest X-ray analysis, where we then even use Jupyter combined with essentially JUWELS modules and then combined with distributed training. So all of this is possible and the details are in the paper. Just a couple of notes that, basically the modular supercomputing architecture works nicely for this mechanistic models, for the parameter exploration. This is research done by Shadi Barakat, or in collaboration with Helmholtz AI, we're working on this COVID-NET, COVID-X data set, which essentially can then classify if people are actually suffering from COVID-19. Also collaboration with the eHealthline company here. And there are lots of more details also in the JUWELS booster paper here that you see that is now available essentially on the archive, and which I could refer to, but we have also very good results. You see here with a very powerful ResNet 152 ×4, which was pre-trained on ImageNet. And all of that means a lot of computation resources have been needed, and the booster was basically used significantly for it. Then from the technology perspective, to give you also this example, the neuroscience lab here in our Icelandic setup, in collaboration again with the Juelich Supercomputing Center and the Neuroscience Institute, we are working on brain data sets. And there we use Jupyter quite nicely with a JUWELS machine online, and also using, as you see here, we're pulling Docker containers for a specific winter school under the umbrella of the Highball project in the Helmholtz community in collaboration with Canada. And this all works also very nicely and is also in detail really described within the paper. Here and there we have some challenges that it not works perfectly. As I was also alluding to here, sometimes this Jupyter could be tricky. We use Jupyter Hub with this, and of course identity management via LDAP, and then a grid middleware called Unicore as basically bridging then these credentials. But the key challenges here and there is much more for us sometimes a module environment that we really have to have the right setup of modules with Horowat, with all the machine learning frameworks to be used in conjunction with these systems. So summary and outlook, just quickly, what we plan is to work in the RACE project much more with different intertwined use cases. This is a recently funded new project with Jülich, Iceland, and many other industry partners. So we will work much more with industry. And here the MSA will be actually used significantly, where one module maybe takes care of the AI and the other module will take care of the numeric simulation. You see here the different use cases. This would fill another complete talk, but you see they are as diverse as coming from computational fluid dynamics up to sound engineering, high energy physics use cases, 3D printing use cases. So lots of different use cases where all different, you see, PhDs will start and we will report on, because all of them will use the MSA intensively. In a way, that's already basically the key essence of my talk. Basically, the talk is at the end here, just a couple of demos of HPC simulations, because I think one of the outlook and summary is really that this modular supercomputing architecture enables maybe industry also to go much easier to the systems. It proved very effectively for our scientific applications, but from our EuroHPC and my EuroHPC governing board member perspective, we have to do much more with industry. So this is one way to solve this and to work with them. Then from the skill set, we see it's getting much more complex. We have interdisciplinary teams which really strive when we're using the MSA. So we need HPC experts, we need AI experts, and then we need the domain specific experts. And to find persons that are all in one is quite difficult. So we see that definitively this teams, and here we're using some research in the race area, basically for this opportunity to find out if we can have, let's say, systematic ways via the so-called interaction room system with my colleagues Matthias Bog and Helmut Neukirchen. Then from the tool set, we have seen JUWELS and MSA with Jupyter Labs, with the container environment Singularity, and then with the traditional setups of MPI, of parallel file systems. This is all basically working nicely, but mastering all of these tool sets together is actually not that trivial, but of course, a way to go if you want to use it for applications. And for us, really, the summary is, again and again, we need more experts in this area that actually can work on all these different domains together. So that's all from me. And you have all the references here essentially in this video, or the talk will be also very soon on my website. With this, I would thank my team, my research group, which really does hell a lot of work on this MSA architectures. And many of the elements that you have seen in this presentations are really their work of the PhDs. And with this, I would like to thank you all for listening to this and talk to you next time.